So we're going to continue with some more review with going over some biochemistry. Hopefully this is at least some review for you since you've taken 3A for chemistry as well as Bio 5 by now. But just in case we forgot, because it could have been a little while since we've taken those classes, we're going to go ahead and do some overview, just reminding ourselves of the basic chemistry so that when we get to those biochemistry points, talking about the physiology of different organs and different systems in place, we are well aware, right, and reminded of the basics. So we're going to kind of try to cover the following things in this video. We're going to go over some basic terms, or at least you should go over these terms on your own: matter, element, atom, atomic mass, atomic number, electron orbital, isotope, and radioisotope. We're going to talk about major and trace elements and what those mean. We'll talk about the basic structure of an atom. We'll also go over neutrons, electrons, and positrons, also known as protons, the nucleus and energy shells, talk about atomic mass and number, and then talk about isotopes and radioisotopes and how those apply to healthcare. So if we just try to remember what chemistry is, it's just the science of matter. So looking at just how matter interacts and with each other, right? Different atoms, different molecules, right? Through what we call chemical reactions. And when we say matter, all we're talking about is something that has mass and takes up space. Mass is the amount of matter, and this is like a one weird kind of thing. So like mass, this is the amount of matter we find in the substance. Weight is a gravitational force acting on the mass. Now on Earth, it's the same pretty much because we are measuring it the same way, but mass will be the same no matter where you are. Weight will change based on where you are in space. So your weight on Earth will be different from your weight on Mars, like the picture here. Now all forms of matter are composed of elements. Elements are just substances that are made of a single type of atom. And the big thing is that we cannot break an element down by chemical means any further. So it's the simplest you can get using chemical means. You can certainly get smaller if you go into physics. However, we are not doing that, right? So we're just talking about the chemical means of breaking something down, the simplest chemical thing we can have, and that's going to be an element made up of atoms. Every element is defined by its atomic number, which tells us how many protons. So, and this is an important thing to note with elements, is that if you change the number of protons, you change the element. That's important because we will see changes in neutrons and changes in electrons, but still have the same element. So neutrons and electrons can change within an element and it's still the same element, right? If we're talking about oxygen, we change the number of neutrons in that oxygen atom, it's still oxygen. We change the number of electrons in that atom, it's still oxygen. But if we were to change the number of protons, we could go from oxygen to nitrogen. So super, super important to remember that, right? Our atomic number of our element is defined by the number of protons that we have in that atom, and that cannot change without changing the element. Most of our bodies are made up of the four elements we see here: oxygen, carbon, hydrogen, and nitrogen. So we're looking at about 96%, maybe a bit over. So a lot, right? A lot of our bodies are made up of those four. And then everything else, because we're not just those four, right? We're other things like iron, right? For example, these are the trace elements. Things that are found in small quantities. We're talking less than 1%, right, in the body. That does not mean that they're not important, right? So they are important, even if they're trace elements. We just don't find them in high amounts. So here's our list, and I don't expect you to memorize the percentage of the body or anything, but you should kind of have an eye on everything that's considered like major elements and everything that's trace. So if you look at this list from phosphorus up, so phosphorus, calcium, nitrogen, hydrogen, carbon, and oxygen, those are all major elements because they're made up of 1% or more. Everything below that, potassium, sulfur, sodium, chlorine, magnesium, right? boron, chromium, cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, selenium, silicon, tin, vanadium, zinc. Like all of these are super, 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 super small. And so those are trace elements. So we mentioned the term atoms earlier, and protons and neutrons and electrons, but we haven't really talked much about them just yet. Remember, atoms is like the single unit of matter that we're going to be using. So this is just the smallest unit of matter that still has the properties of an element. Because it's important to note each element will chemically react differently, right? It's going to react and form different types of bonds and all this kind of stuff differently and uniquely. So oxygen is going to have different properties than nitrogen, for example. If we look at all of the atoms for oxygen, they all act the same. If we look at the nitrogen atoms, all the nitrogen atoms act the same, but the nitrogen and the oxygen atoms do not necessarily act the same. So atoms, they have the properties of their assigned element. They're electrically neutral, and they have 3 subatomic particles. We'll talk about electrically neutral in just a second. But the 3 particles we have are the protons, the neutrons, and electrons. Protons have a positive charge. Neutrons have no charge, they're neutral. Electrons have a negative charge. So we see we have a positive, no, and a negative charge. This is why we say we're electrically neutral, because the positive and the negative cancel each other out. Now, the protons and the neutrons are found in that nucleus, while the electrons are going to be found in electron clouds spinning in orbitals around the nucleus. When it comes to their mass, protons and neutrons have the same relative mass of 1, but electrons are so small and so light that we basically don't include their mass in our calculations for this class because it's so small, it's inconsequential for us. So I mentioned that these electrons are floating around these orbitals, right? Sometimes they're called orbitals or shells. These are just basically energy levels. And really there's one big thing out of this. If you're reading through this slide as I'm talking here, there's one major thing that I need you to remember for this particular topic. And that is the valence shell. The valence shell is the outermost shell. And all atoms have a desire to fill their valence shell. Now, if you're really small, like hydrogen, you only have one small shell that can fit 2 electrons max. But the shells that come after that for other atoms, like oxygen, their shells on their valence shells can hold 8. And the reason we're going for holding the maximum number of electrons for the valence shell is that this creates stability. So these atoms are trying to find stability, and they do that by filling their outer shell, their valence shell, with electrons. And they can do that through chemical bonding. And we'll talk about chemical bonding next. So before we get into chemical bonding, because that's going to be the video that comes after this, we have a couple ways we can describe atoms. We have the atomic number and atomic mass. Atomic number is the number of protons. This number defines the element. So let's say we look at carbon. Carbon has 6 protons, so its atomic number is 6. We will always have 6 protons as carbon. Always, always, always. If that changes, then that means that we have changed the element. So if it were to have 7 protons, we would not be carbon anymore, we would be nitrogen. We use the atomic number to organize the periodic table, so you see that picture below. And then you'll also see a number that is close to the atomic number, but not exact, and that's the atomic mass. So we look at in this picture here, we see hydrogen has an atomic number of 1, but it has an atomic mass of 1.01. And you're probably thinking, well, where does the 0, 1 come from? This is because we're looking at the number of protons and neutrons in the nucleus and we're looking at the average mass because we're including isotopes. Isotopes are going to be atoms of the same element that vary in terms of their number of neutrons. So protons must stay the same, right? They have to stay the same in order for it to be the same element. But neutron number can vary a little bit. So our atomic mass is the average if we look at all the isotopes. So it'll never really be a perfect clean number. Something else we need to remember are ions. Ions are atoms that have gained or lost electrons, and so they do have a charge. Because we have changed the number of electrons, we have either created a negative charge or a positive charge. If we gain electrons, right, we've added electrons. Electrons have negative charges, so if we add more, we end up with a negative charge. If we lose electrons, now we have more protons. In comparison to the electrons, we now have a positive charge. So here's just a couple examples. We see a chlorine ion with a 1 negative, so we have one single extra electron there. And our second example is calcium. We have lost 2 electrons, and so we are Ca2+. Now, I mentioned earlier elements that have the same number of protons but different number of neutrons are called isotopes. So we kind of mentioned it and talked about it a little bit, but we're going to go ahead and look at an example here. So like here in this picture, we see these 3 different carbons. They're all carbon, right? And the reason we know they're all carbon is if you look in the middle, right, in the writing that's down below the pictures, we see how many electrons, protons, and neutrons they each have. If you look across the board, every single one of them has 6 protons. That's big, that's important. Because 6 protons tells us carbon, right? 6 protons tells us carbon. If we change the protons, we're going to be a totally different element, right? We change it to 7 protons, 8 protons, now we're nitrogen, oxygen, whatever. But if we look at the bottom there, we see the neutrons have changed from 6 to 7 to 8. So we have carbon 12, which is like the standard normal carbon, right? What we think of when we think of carbon on the periodic table. Carbon 13 has 1 extra neutron, so we've changed our nuclear number, and thus we've changed our atomic mass, but it's still carbon. And then we get to carbon 14, where we have 2 extra neutrons, right? Still carbon, but we've added these 2 extra neutrons, which in this case does lead to radioactivity, meaning carbon 14 is not going to be very stable. It is going to break down. Generally, that means it's going to emit neutrons until it goes down to like carbon 13 and 12. So isotopes, so like we're looking on the back slide right here, right? We see the different isotopes, and we saw that there were some who are stable and some who are radioactive, right? Because they were unstable. So like C12 is an isotope that is very stable. It doesn't really break down, it just kind of does its thing. Versus carbon 14, unstable. It's going to emit what we call radiation. Now, we're not going to get into the different types, alpha, beta, gamma radiation, but the big thing is they break down, which means basically things are going to be flying off of those isotopes, and they're doing that until they reach stability. Now, because they're unstable isotopes, we call them radioisotopes because they're radioactive isotopes. Some of these can be harmful, right? If you're exposed to radioisotopes, can cause cancer, can cause your cells to die, but we can also harness radioisotopes for our own benefit. So we do see these being used in like nuclear medicine. So for example, there's radioisotopes of iodine that can be used for imaging of the thyroid, since the thyroid pulls up iodine in high amounts. So that was just one example, but here's some other ones as well. So looking at nuclear medicine basically is just the use of these radioisotopes to help with diagnosing a disease, and this includes helping diagnose things like cancer, injuries, infections, right? But basically we give a radioisotope to the patient, and so this radioisotope, when it gets taken into these tissues, is going to start to break down because it is radioactive. It will decay. We emit radiation, and then we can use machinery, we can use tools to detect that radiation that can be captured and converted into an image. The isotopes that we use for imaging tend to be lower energy emitters because we want to minimize risk. Because they are radioactive, we want to make sure that we are not giving anything that's going to be too harmful. We do want the pros to still outweigh the cons, right? We can also use them therapeutically. So the biggest one is cancer. So radioisotope-based therapeutics are used to kill cancer cells because cancer cells are highly proliferative, meaning like they're going to go and divide and divide and divide and divide. When they take in these radioisotopes, it can trigger the cell to die, right? So we can basically use these radioisotopes to sneak into cancer cells and kill them. And then higher energy emitting isotopes, these can be used to kill cells in general. So these are just a few things that we can use these isotopes for in medicine, right, that have a benefit.